Yeah, so I'm Alan Chakas. I'm with Neptune, which is a new layer one cryptocurrency big on privacy and post-quantum security and scalability. And in Neptune, we are using TritonVM as the go-to zero-knowledge virtual machine. And since Neptune, one of the selling points of Neptune is scalable privacy, and that's the topic of this talk. Mutator sets is a key technological component alongside TritonVM, and it is responsible for our claim to scalable privacy. And so that's what I'm talking about. Here's a little bit of a table of contents, but really most of this presentation is slightly more disorganized than the presence of a table of contents would suggest. It's more of a stream of thoughts, steps that do follow logically one after another, but we try to categorize them into a table of contents, and that doesn't really work. So maybe I should just cut this slide, future presentations. So we're dealing with blockchains where we want to transmit tokens, coins, money, and in order to verify that they have been transmitted, what you need is the UTXO set. UTXO set is the database of all spendable coins. And so if you possess this database, then you can check very efficiently whether an incoming transaction is actually spending one of the coins in this database. And the beauty of the blockchain is that it recreates this data set across the computers of all participants in the network. And so there's this huge research topic around consensus. The objective of consensus is to make sure that everyone agrees on what this data set contains. And the point is that it's not fixed. It changes over time. There are many, many old versions, and we really only care about the new version of the UTXO. We do care about old versions, but only as a means to verify that the new current one is correct. And so the way we use it is we broadcast a transaction, and this transaction is the rectangle. The transaction consumes coins from the UTXO set, and it produces new coins. It mints new coins. And after the transaction is confirmed, then the new coins live in the updated UTXOs. And that happens again and again. So a new transaction happens. It consumes coins that live in the UTXO set, and it produces new coins. And this picture actually already shows what the problem is. Because whenever you spend a coin that was necessarily produced previously, it is very easy to verify that these two coins are the same. It's very easy to link them together because they look exactly the same. It's no work at all to link them together, and this is terrible for privacy. And so that's the link that, as a privacy architect, we need to find a way to break or obfuscate. And so every privacy-oriented cryptocurrency has a way to obfuscate this. Concrete architectures differ. I'll be covering our architecture. So, except for a handful of privacy coins that exist, almost all cryptocurrencies are transparent. You can look at the UTXO set. The UTXOs don't do any hiding of data. And so while that is excellent for auditing, making sure that whenever someone claims to own a set of coins, you can verify this. It's very good for verifying that transaction and don't spend more money that is coming in. But it's terrible for privacy. And so the zero knowledge, the privacy coins using zero knowledge proofs can actually make this opaque, whereby you don't get insight into which coins are being transferred, what the value of those coins are, and so on. And the beauty of zero knowledge proofs is that you don't have to sacrifice auditability. You still have cryptographic assurance that the books match, but now you also have privacy. But zero knowledge proofs alone are not enough. You need something more than zero knowledge proofs. And so this is taking the first step towards the construction that will be mutator sets. We want somehow the things that are being consumed by transactions and the things that are being produced by them to look completely different. And so we want, in the language of mutator sets, or in the language of the paper, we call these removal records and these addition records. Because whenever you have a transaction, the inputs to the transaction are removed from the UTXO set, and the outputs of the transaction are added to the UTXO. And so we're looking for representations of UTXOs or of coins. Whenever I say UTXO, you can hear in your head coin. We're looking for representations of coins that depend on which side of the transaction is being used. And that's the origin story of the name mutator set, because it contains a set of UTXOs, but their representations mutate. And furthermore, we want these representations to be cryptographic commitments. So you should not be able to equivocate and say, this is a addition record or a removal record that pertains to this coin, and then later change your mind. If you do change your mind, you will be unsuccessful. That's what it means for it to be cryptographically binding. We also want it to be ID because of privacy. And so I guess the color scheme indicates that this addition record and this removal record are both linked to this coin. But the point is that since they have different shapes, you cannot link them. That's the very abstract ideal construction that we're looking for. And we can get a little more concrete. We can actually start defining features that we want the ideal mutator set to have. So this is a cryptographically authenticated data structure. Think of Merkle trees, but with fancy properties. You can put items in, and you can take items out. And whenever you put something in, the thing that is visible to the rest of the world is the addition record. And whenever you take something out, the thing that is visible to the rest of the world is the removal record. But you cannot inspect items. You cannot remove items that aren't in the set. And you should not be able to link additions to removals. And if you have all those, then we're also going to require scalability, which I'll define later. But the point is, it's rather easy to find a construction that does all but one of these features, but if you want all of them, then it's a little more difficult. And so here's a construction that fails in terms of scalability, but actually achieves all the other properties. And this is essentially the same construction that was proposed 10 years ago, I think, in 0 Point, the paper, then repeated again and again in Zero Cash, Monero, and so on. The idea is we still have removal records and addition records, except now they're called nullifiers and notes, transaction output commitments, coins, whatever the name is, it doesn't matter. It does map onto this mutator set formalism. But in addition to the removal records going into a transaction, there's a proof that goes into a transaction. By the way, in mutator sets, there is also a proof that's going into the transaction, but this proof doesn't just prove that the books match, that the amount of incoming coins is the same as the amount of outgoing coins. It also proves that the nullifier was derived from some earlier addition record, and that the nullifier was not used previous. This is how you catch double spending attempts. If your cryptocurrency is privacy preserving, how do you catch double spending attempts? How do you prevent people from spending the same coin twice? You have to catch them somehow when they try. And the nullifier is what does this. Whenever you take some item out of the mutator set, you are required to broadcast a short cryptographic string that uniquely identifies that item. That's the nullifier. And whenever the same nullifier is being broadcast twice, then you can notice the fact that a double spending attempt is happening, and you can reject that transaction. But that's a bit of a problem, because you could totally compress the transaction output commitments or the addition records. You just put them into a Ripple Mountain range, but there's no way to compress the nullifiers, because either the transaction initiator needs to possess the entire list, or the transaction verifier needs to possess the entire list. There's no way to compress this at all. And this is why the decoy and nullifier set construction doesn't scale. The nullifier set keeps on growing indefinitely. If the network is twice as old or processing twice as many transactions, this set is going to be twice as large.
Yeah.
Please.
So the passenger is only we don't know the owner of each of the token, or the other people don't even not see how many tokens they distribute as well.
So both the additional records and the removal records, they uniquely identify UTXOs, and every UTXO has an amount, but you cannot read the amount from the transaction. But in addition to this zero knowledge proof that shows that the nullifiers are new, there's another zero knowledge proof that shows that the amounts that go in equals the amounts that go out.
Confidential transaction. So when you define compress, you mean you hope that the amount of storage we need only depends on the number of distinct accounts rather than the historical transaction.
Exactly. Yes. Well, in fact, it would also be nice if the number of storage that we need was less than the number of active accounts. If you could only take care of your own account, and if the system works, if every user takes care of their own account, that would be ideal. But in this construction, you have to take account of all of history. So that's very far from ideal. Yes, by the way, please do interrupt me. I love getting feedback from the audience, and I don't mind digressing. So, 2 words, an alternative construction from the one on the previous slide. We can use bloom filters. Bloom filters are already used in Bitcoin, not for privacy. They are used in a more abstract sense, both in Bitcoin and elsewhere, as a way to accelerate databases by giving you a probabilistic answer as to whether an item is present in the database. Then if you know it's present, or if you know it's likely present, then you can actually look at the hard disk and read the file and so on. And that's the expensive part. But if you get a null answer, then you know you can report early and send back, sorry, this item doesn't exist in the database without having to look at the hard disk. And the way the Bloom filter works is we hash the item using k different hash functions whose output could be k different or possibly different indices in a large bit array. And this bit array is initially 0. And for every item that lives in the Bloom filter, you set all the bits indicated by its hash function. So in order to represent the Bloom filter, you just represent the array of bits. And then in order to perform this probabilistic membership test, you hash the item k many times and you look at the indicated bits. If one of the indicated bits is 0, then you know with absolute certainty that the item was never inserted into the Bloom filter. So you can abort early. But if all items, if all indices are set, then it's possible that the item was inserted and you have to look more closely. So the probability of a false negative is 0, but the probability of false positive is different from 0. And there is, in fact, a well-defined mathematical expression that gives you the exact false positive probability. And by tuning the parameters, you can make this false positive probability negligible, cryptographically negligible, and hence secure enough to keep track of some kind of changing sign. So in this expression, we have E, that's the what is it? It's not Euler's constant because Euler's constant is something else, but it is you have pi and E, one of those two constants. Right? K is the number of hash functions, N is the number of members in the database, and W is the number of bits in the array. So you can imagine you can stretch the array, then you have a larger capacity for accumulating items. Oh, and by the way, speaking of capacity, as you insert items, at some point you're going to saturate your bit array, and you're going to get false positives nearly every time. So there are parameters K and W that are optimal for a given N. And so that's not really useful for what we want because the number of UTXOs that we want to keep track of should be variable. Bloom filters inherently have a finite capacity. And so, well, it's cool that we can repurpose it to achieve something cryptographic in nature. We have to get around to the finite capacity. Okay, so we slide the Bloom filter. We implicitly define an array of bits of infinite length, but for every item that we insert into the Bloom filter, we only look at an active in window, which is a part of the Bloom filter, and periodically this active window slides. So this makes it rather useless as a membership test because you would need to know the position of the active window at the time that the member was inserted. So unless you know when the item would be inserted, if it had been inserted, then you can use it as a membership test. But if you don't, it's a pretty not very useful as a membership test. But that's okay because we can record that timestamp. Just need to find a way to work with it. Okay, next up. Here's how we achieve a basic mutator set. So we are keeping track, in fact, of two sets. One is the set of all addition records, and one is the set of all removal records. Or phrased differently, we're keeping track of the set of all additions and the set of all removals in two separate constructions, separate but linked. So in order to record an addition, we just add the commitment to the item to a list of commitments. It's the append-only commitment list. This is only ever going to grow. And so when we append an item, we hash it after we concatenate some randomness, and then we hash it, and then we have a timestamp, an index of insertion into this list. Right. And when we want to remove an item, say we want to remove this item, we know that it corresponds to a timestamp, its index. And so we have to show, firstly, that we know the item that gave us this commitment. And secondly, we can use the timestamp of that commitment in this list as the timestamp for this Bloom filter test. And so using that timestamp, we actually know which window to look in. And then we look at those bits. And so the removal record is just a sequence of bits, but that's not enough because it should be difficult to remove items that do not belong to the set. So what's missing is some kind of process that makes it difficult to publish a list of bits if they don't correspond to an item. And that's what the zero-knowledge proof does. So this entire derivation happens inside of a zero-knowledge proof. So in fact, it proves that you know the item that corresponds to some commitment in the list, and that for the timestamp of that commitment, you've derived these bits. This process is entirely deterministic, so every item uniquely determines these bits. And since there are enough of those bits, every set of bits uniquely determines the item as well. This is the basic construction, but it's not scalable yet. But scalability we can add later, and I'll show that construction then as well. For now, let's look at privacy, because the privacy is not perfect. The thing that you need to link if you want to break privacy is you need to be able to link removal records to the vision records that generated them, because they correspond to the same item. And what you get is a fuzzy timestamp, because you can look at a sequence of bits and there are only a finite number of windows in which those bits could lie. And so that means that there are a finite number of timestamps that could have generated a sequence of bits. So you have a fuzzy timestamp. And as a result of having a fuzzy timestamp, you have a distribution of plausible origins. And so in the ideal case, this distribution would be uniform across all addition records, but in our case, it's not. So in fact, we can look at the entropy. Take note of the camera, don't walk for it. We can take note of the entropy, which is information entropy of the distribution of plausible origins. And we can plot the entropy with plot the frequency of observing a given entropy as a function of a bunch of parameters. And in fact, these are the parameters that we use in Neptune. The window size is 2 to the 20 bits. Patch size is 8. Step size, how much the window shifts, is 2 to the 12. So after 8 additions, the window shifts by 2 to the 12 bits, and k is the number of hash functions. And so I've also, hang on, since the batch size is 8, your anonymity set is always at least 8. So that's why this graph doesn't drop below 3, which is what we're in base 2 with 8. But in fact, the entropy that you're getting is higher on average than 3. And that's computed experimentally. And entropy, experimentally speaking, is slightly larger than 5, which corresponds to an anonymity set of 32 in the geometric mean. This is the information entropy of this probability distribution. And this is the frequency is how often do you observe a distribution of that entropy. X-axis basically measures the level of privacy that's being crossed. Yes. So you want to be as far as possible in this direction. And
so when you say entropy is 5, it's 5 bits.
5 bits of entropy.
It means if your account is indistinguishable from 31. Oh, okay.
That's the entropy, the definition of entropy.
Gosh.
Exactly. Okay. Now let's look at scalability. We can look at how the threshold costs evolve as a function of parameters, and now we're looking at number of additions and number of removals at the time that the item was added, and the number of operations in between adding and removing. So the basic mutator set is very good for adding because you just broadcast your item. It's not very good for removing because you need to prove membership in a very large list. And in order to verify that proof, you need to read the very large list. And in order to verify, in order to prove the correct derivation of the list, you need to touch every member of that list. But in order to verify it, you don't just need to touch every member of that list, but you also need to touch every removal record and every operation in between. But fortunately, there is a trade-off. We can improve on the 2 bad metrics at the expense of making the addition slightly more expensive and introducing another column. So whenever you own a UTXO, now you are responsible for updating the witness that attests to membership in the mutator set. Fortunately, that's still a very manageable cost, but it's more than 0. So in exchange for introducing this cost, we get to shrink these the cost of removing and verifying. And I'll show you how that's done with trees and
Just when you say update reports, you mean the client needs to stay online to update the report?
he either needs to stay online or once he is back online, he needs to catch up.
Okay.
Let's see. So Merkle trees. The idea is we have a bunch of data points called leaves, and we want to compress this into a single data point called the root. And we do that by hashing in every layer. We concatenate 2 items, 2 nodes, and hash that, and that gives us the node in the next layer. Do this repeatedly, and you get a tree structure like this. And then we can say the bottom set of nodes, those are leaves. The top node, that's the root. Then we have here a path from a leaf to the root. And if we look at all the siblings on this of nodes on this path, it's the yellow nodes. That's the authentication path. Now you can verify my claim that this leaf belongs to the tree defined by that root if I give you the authentication path, because you have exactly the right pre-images to the hash functions, to the hash function. So if you recompute the hash function step by step, you will rewrite the same root, thereby verifying my claim that the leaf is present at the given index. Okay, that's nice. But what if you Merkle tree? Importantly, the height is the grows with the logarithm of the number of elements, the number of leaves. That's great. But what if you don't have enough memory to store all the data items? Well, then you have to find a way to stream, to produce this Merkle tree in a streaming fashion. And so that's one interpretation of Merkle mountain ranges. You can define your intermediate state as you compute the Merkle root of a very large data set that doesn't fit. Intermediate state is a sequence of progressively smaller trees. Roots, even, because once you've computed the root of a small tree, you're going to drop all the leaves. And you can compute it in a streaming construction whereby you read the leaves one by one. And whenever you read a leaf, you do something. And what you do is this. You cut the leaf, and whenever you have two nodes that you can merge, you merge them and forget the nodes. So append and merge whenever possible. So suppose we are at this point, we've read all of these leaves, and we've computed our Merkle mountain range, and we read the next leaf and observe, and now we can merge. So we merge and forget. And observe, once again, we can merge and forget. So we merge and forget. And once again, we can merge and forget. And boom, now we've reached the next state of the streaming algorithm, whereby we can read the next leaf. So you can think of Merkle mountain ranges as a way to build very large or even infinitely large, perhaps indefinitely large Merkle tree. Which is useful if you only have a logarithmic amount of memory available. And so, how do Merkle mountain ranges improve our construction? Well, for starters, we want to get rid of this huge list, and we want to represent it as a Merkle mountain range. AOCL MMR stands for the append-only commitment list Merkle mountain range. And secondly, in this sliding window Bloom filter, we want to record the active part explicitly because that's where most of the activity is expected to happen. But the inactive part, that's for old UTXOs, which are only being spent relatively rarely. And so we want to chunk that into subsequences of bits, and those chunks go into another Merkle mountain range. So the sliding window Bloom filter consists of a Merkle range and the active window. And so, what information do you store if you run a node? The answer is you store the peaks of the append-only commitment list. You store the peaks of the sliding window Bloom filter, and you store the active window. This state set grows logarithmically with the number of MTXOs either in history or in the data set. By the way, this is the slide that you'll want to take a photo of if you are so inclined.
I'll probably make sure that a transaction currently spending is not being spent
If it has been spent before, since every UTXO uniquely identifies set bits, you'll notice that the bits that are indicated are already set. So in order to spend a UTXO, you have to have, so to spend the UTXO, you broadcast the removal record, which consists of a set of bits, and it's only spendable if at least one of the bits has not been set yet.
So at the bottom line, the Mutator actually has different states. For each bit, it could be empty, unspent, and spent. Three kind of states.
No, 0 or 1.
But how do you record three different states with only one bit?
Because when you add an item to the mutator set, you don't touch the sliding window bloom filter. You only touch the sliding window bloom filter, or excuse me, you only change the sliding window bloom filter when you remove items. Initially, the bloom filter is all zeros, and you set bits only as you remove items.
Then how do you remember which items have, which transactions have been, or which outputs have been added?
That's what the append-only commitment list is for.
But it said it only so the top of commercial mountain ring, they are acetate, express are connected. But the bottom the local mountain rings would be updated when the coin is spent.
Yes, and so that's the reason why there's a trade-off between the active part and the inactive part. You need to make sure that the size of the active window, or at least the size of the portion that is represented explicitly, captures active user activity, because you want to, because you're correct. When an old UTXO is being spent, you have to update the sliding window, and you don't want to have to do that often. You prefer all the activity to happen in the active part, because that's where you don't use any compression.
So each square on the above is actually a transaction.
No, each square on this line
On
is
the append only commitment.
each square here is a digest.
Oh, it's a commitment.
It's a commitment. Okay, you think so? Yes.
And mine is
So we can compare this privacy architecture to other privacy architectures. And there's unfortunately a lot of nuance that gets lost once you try to force architectures into a format that's amenable for comparison. So please take this with a grain of salt. And also note that there's a whole bunch of parameters, and depending on circumstances, some parameters can be more important than other parameters. So let's look at 3 tasks and 1 question. The tasks are initiating a transaction, verifying it, and updating it. So think user, minor, user, where updating is what you need to do as you remain online continuously, or the task of catching up if you spent a portion of time offline. Initiating is the work you need to do after you've decided that you want to make an expenditure. And the trust assumption is, are you implicitly assuming the trustworthiness of public places? So I have a bunch of architectures here. Some of them don't exist, but for the sake of comparison, it makes sense to be explicit. And so the very first nullifier on this list, that's the very first privacy architecture in this list is the decoy and nullifier scheme that I already touched on in this presentation. And I observed that you can actually improve on that decoy and nullifier scheme if you use cryptographic accumulators and integrate into your nullifier derivation a snapshot of the state of the UTXO set. To my best knowledge, that doesn't exist, but it could. Then there's Mimblewimble, which uses essentially confidential transactions and coin join and cut through. Then there's mixing, which is, hang on, there are two types of mixing. In first type, you charge miners with mixing all of the UTXOs that were confirmed in that block. And in the second type of mixing, you mix yourself, your own transaction outputs with random selection of UTXOs in the UTXO set. Then there's mutator sets, and after writing the paper, but before creating this presentation, I was made aware of another architecture that's in fact used in Turing. But that only works in the account model. But if you are working in the account model, then you might as well make your accounts, you might as well format them as additively homomorphic ciphertext. And then you can add 0 to a bunch of decoys and the money that you're actually transmitting to the one destination, along with a zero knowledge proof that you're not producing money out of thin air, and the observers won't be able to know which one of the touched accounts are actually the recipients. And so here's the cost picture. Let's look at the big terms. In the decoy and nullifier scheme, somebody needs to store the whole nullifier set. And if you use snapshots, you need to keep track of all the nullifiers that are being published after your UTXO is confirmed. So this is much better if the privacy cryptocurrency is used in a transactional manner, and as in very shortly after receiving the coins, you spend them again, then it's fine. But if you want to sit and hold for a long time, you're going to have a very tough job once you resynchronize with the network. In Mimblewimble, I would argue that there is an implicit trust assumption, or at least if you use it properly, right? Because there is no construction for breaking the links between transaction inputs and transaction outputs. Because as a node on the network, you can observe transactions as they are being broadcast. If you want to find which UTXOs belong to which transactions, then you need to bundle your transaction with other transactions, or you need to charge someone else to do that. And as soon as you charge someone else to do that, to improve your privacy, well, then you're implicitly trusting that they are not putting decoys into that bundle. Then if you're going to trust the miners to do mixing for you, then obviously you have a implicit trust assumption with the miners. And in this case, if your architecture is such that every transaction initiator includes their output UTXOs into a mix, well, then there is necessarily a likelihood that the UTXOs that you own are included in the mixes of other people. And that means that you have to trace UTXOs across all of those mixes. That gives rise to a tracing problem or tracing task. Homomorphic accounts as Infern uses, it's assuming that the accounts exist and are being managed as a byproduct of the miners or stakers on Ethereum doing their thing. But if you take that cost into account, well, cost is actually linear in the number of accounts. And then here for mutator sets, we do have this cost that's linear in U, which is the number of operations in between. No, hang on. U is the number of UTXOs that were confirmed before yours. But this is very much a worst case here, because not all UTXOs that were confirmed before yours will be spent. And moreover, this log L is also worst case because the log L determines, it captures the cost of having to walk up the entire Purple mountain range, and most of the time you don't walk all the way up. All right, let's move towards a conclusion with 2 more slides. You can plot 2 important dimensions and put existing architectures on this plot. And I'd say maximizing in terms of scalability with 0 privacy, that's where you find constructions like U3XO. Where you have a UTXO set that's compressed with cryptographic accumulators. And yes, it does charge users with updating their Merkle truth. But in exchange, you get really, really light nodes. And on the other end of the spectrum, you have a very poor scalability, but maximal privacy. And that's what you get with decoy and nullifier sets and an infinite ring size, where infinite is essentially all other UTXOs. That would be the construction that Zcash has, and then Monero doesn't have an infinite ring size, but still a large one. But on this plot, mutator sets, well, I put it near the origin to articulate the inherent trade-off, but actually I'd say it's rather more scalable than where it's currently located. But it's certainly less scalable than U3XO and less private than Monero, or maybe equally private as Monero, but less so than Zcash, because the ring size is definitely not infinite. Phrased differently, the anonymity set is definitely smaller. And it would seem as though it's because of this tension between privacy and scalability. And I would go so far as to argue that this tension is the wrong way of thinking about it. Because privacy is only meaningful if there are crowds. And you can only support crowds if you can support a large number of users. And so you need scalability to make your privacy meaningful. If I had to reduce this dilemma to a short phrase, I'd say it's not worth hiding behind the 3 other users of your privacy core. Even if that hiding is perfect, it's much better to hide weakly behind 3 million users. So mutator sets definitely have the application to make blockchains private without sacrificing scalability, but they also have other applications. For instance, anonymous dynamic ring signatures. A ring signature scheme is where we collect a bunch of public keys and produce a signature that's valid under one of them on behalf of the group. And we're not linking under which one it is valid. So you only get a signature from the group as opposed to from an individual. And the property, the feature that mutator sets can add is they can obfuscate who is a member of the group who isn't, because you can join and you can leave. It will be difficult to track who joined, who left, who joined again. So the group itself is anonymous now, but still cryptographically authenticated. You can have anonymous revocable credentials, such as people with access to a database where you need to show a digital equivalent of a badge. And then the question is, who has access to this database? Well, you can have a mutator set, and then it will be very difficult by design to answer this question, because people can join, they can be kicked out, they can leave, and you don't know who. And you can have private electronic voting, because whenever you have a credential system, you can use that credential system to authenticate your eligibility to vote. So you can cast that vote, and if you don't know who is eligible, then you have private voting. And it's rather nice and surprising that we have a construction for electronic voting that doesn't involve any hardness assumptions that are typically used to build public key encryption. In terms of open questions, mutator sets as designed in this paper and articulated in this presentation, they require two cryptographic ingredients, hash function and generic zero-knowledge proof. Well, I say generic, but the zero-knowledge proof is actually highly specific with a rather involved computation. But in practice, by the way, we have an implementation of all of this. In practice, this generic zero-knowledge proof is produced by Triton VM, whose only cryptographic ingredient is the same cryptographic hash function. So it's perfectly valid to say that the only cryptographic ingredient used in practice is the hash function. And since hash functions are not known to be attackable using quantum computers, it means that this scheme is plausibly secure against quantum computers. However, we don't have a proof yet. That might be an interesting master's thesis topic, if you know of anyone who might want to do that. Secondly, the features that this construction brings about might be improved upon if you drop the hash function instead in favor of some kind of number theoretic construction, reintroducing that hardness, cryptographic hardness assumption that's typically tied with public key schemes. Maybe with one of those cryptographic hardness assumptions, you can actually improve privacy and scalability somehow. So I think with that, I will close. Mutator sets occupies a point on the trade-off curve between accumulators with scalability and decoy and nullifier sets which do privacy. You were listening to the voice of Alan Gatz. This closes my presentation, and then now open the floor for questions.